Hello everyone, how are you all? I hope you are doing wonderful. So in this presentation, we're going to be talking about NURBS Curve. My name is Sirsha Banerjee and I'm a third undergrad from IIT Kharagpur. Let's get started. So in this lecture or this presentation, we're going to be talking about NURBS, which basically means for non-uniform rational B-spline curve. So our agenda will be discuss the understanding of NURBS curve. Along with that, we're going to be also see how we can implement that using a MATLAB code. We will trying to make a circular arc using 3 contour points and accordingly we will choose a weight function. Also, we will be seeing how we can plot a circle using 7 contour points and accordingly we will change our weight functions for each of the points. So this video we're going to be also talking about the MATLAB code demonstration. Alright, so let's get started. So as you all know that rational B-spline curve is the projection of a non-rational or a polynomial B-spline curve in a 4-dimensional homogeneous coordinate space back into 3-dimensional physical space. So we can parametrically define the curve as a summation of the control points multiplied with the blending function of the B-spline curve. So where BIHs stand at the 4D homogeneous defining polynomial vertices for non-rational 4D B-spline curve, and NIK of t is the non-rational B-spline basis function. Previously we have already seen how we can plot a normal B-spline curve. So in this presentation we're going to be seeing what is the difference of a NURBS curve. So projecting back into a 3-dimensional space by dividing through the homogeneous coordinate field yields the rational B-spline curve, as you can see over here. So from this particular presentation we're going to be trying to implement the same in the MATLAB code. Let's see how we can do that. So what I'm going to do, using the 3 contour points, I will be choosing h1 and h3 equals to 1, and based on the value of h2 that will define that what kinds of conics we can draw using a NURBS curve. So here it is listed down below that if h2, that is the weight function or the weight associated with the second control point, is basically equal to 0, then we get a straight line. Similarly, if h2 lies between 0 and 1, we get an ellipse. Similarly, if h2 is equal to 1, we get a parabolic curve, and similarly h2 greater than 1, we get a hyperbolic curve. So let us, if we substitute back t is equal to half in this particular equation, from here we get this particular notation. And also let us see how we can perform these particular circles using the equilateral triangle or maybe a 490-degree segments like a square. Alright, so let's jump back to the MATLAB demonstration. Alright, as you can see, the MATLAB screen is open. So let us see and go through the code for the first time. So this is a code for NURBS curve implementation using a mouse input for control points and keyboard input for the weights. So I have used the inputs from the mouse for the points and the weight inputs is to be given by the user. So first of all, I'm writing how many control points we need to give. That is a user input. So you can see over here the code basically talks about you have to input the number of control points. So once we get the control point, using the mouse command, we will be basically trying to plot that control point. So where you can see that I have taken the input using the mouse click as a G input. Alright, and I have plotted all the points. Along with that, I have joined all the control points so as to make the control polygon. Now I have taken the inputs of the weight from the user, as you can see over here. And with that, I have also asked what should be the degree of the NURBS curve. And once I get all these data, I have tried to calculate the knot vector based on this. And based on this, I have implemented the same thing using the for loop. So where you can see the parametric curve has been presented over here, where the numerator is the sum of the weight function into the control points into the basis functions, and the denominator is the weight multiplied with the basis functions. And once we get that, I'm calculating the point by sum of the numerator divided by the sum of the denominator, as we can see over here. So once we get that, what I'm doing, I'm plotting the NURBS curve. Now you might be wondering how I calculate the basis function. So for calculation of the basis function, I have used the Cox-de-Bourg recursion formula. So from where we can see that for the given spline, we have to calculate the basis function as per the recursive definition. And I have implemented the recursive definition and I have get the output as n with the following input as I, p, u and knot vector, where I have provided u as the parameter. So based on this, I have calculated the recursion formula for getting the basis functions. And once we get the basis function, this particular basis function will be returned over here, where we will be using that to calculate the NURBS curve. So let us see the working of it. Alright, so the code is asking me for the number of control points, and I will be trying to implement the following as 7 control points. So if I give 7 as input, then the code will be asking me to click on the input control point. And as you can see, this is my mouse cursor where I can move and I can choose the control points. So I will be choosing a equilateral triangle control point. So I will be trying to make that. So let's see how well I can do it. And so yeah, and this is the 7th control point which I am providing as the same. So you can see the control polygon is drawn as shown. So by the diagram you can see, observe that it is not a proper equilateral triangle, but still I have tried to get the inputs from the mouse. Let us see what are the weight function corresponding to that. So if I provide the weight function for the first point as 1 and corresponding as 0.5 and 1 and 0.5 interchangeably, we will basically get a closed curve, and we will trying to get a circular or a circle. So let us see, and we enter the degree of the NURBS curve as 2, and therefore the curve is drawn. So you can see over here the curve is drawn, and this is a closed curve. So based on this, if you try and change the control points and accordingly you adjust the weight function, you will definitely generate the different conic sections. Let us see how we can implement the ellipse using 3 control points. So I'm closing this and I'm rerunning the code again. Yeah, so if I'm putting 3 control points this time, and then I choose the control points as a triangle input. So like this, I'm choosing the control points. Alright, so once I get the control point, now it is asking me for the weight. So for the first one, I'm providing weight as 1. For the other, I'm providing as 0.5. And the last point, I'm providing the weight as 1. And I'm providing the degree as 2. So with this, the curve is drawn. So what we can see over here, this is a part of an ellipse, because what we understood is that when h2 is lying between 0 and 1, for this kind of 3 control points, we get an elliptical curve. And we all know circular arc is basically a special case of an ellipse. So yeah, that is it. So with this, we jump back to the theory, and what we see, we have tried to implement the same. So we saw that how we can implement the same circular arc using a NURBS curve. And with this, you can also see this particular thing that I was talking about, that for using a 3 control points and by choosing the values of h2, we can definitely get to the various conic sections, as we can see from here. So that's what I have tried to implement then the same in the MATLAB code. Alright, so that was all about the today's presentation. Thank you for your attention.